Okay, so this one talks about a rigid motion. So we have to remember what rigid motion means. And rigid motion means it preserves size and shape. So are these two the same size and are they the same shape? They are. So this is a rigid motion because all the corresponding angles and all of the sides appear to be the same size. It doesn't matter if they are rotated or if they are reversed, as long as they're the same size and shape. Now, one other note here is that we have an image and we have a pre-image. The pre-image is the first image, and then the image is the translated or transformed image. So once I move it, this is my second image. So pre-image is the first thing, and the image is what we move it to. All right, now this one is not a rigid motion because we did not preserve size and shape. We did preserve size, but the shapes are changed. So this is a dilation of the original image. So again, this is the transformed image right here. It's a dilation, means that I stretched it or I blew it up or I shrunk it. And then this is the pre-image. So this one is not a rigid motion because the corresponding sides do not appear to be the same size. Now on this one, I think we're on number 3 now. This is asking for the reflection. So I see it says the reflection of the image across the given line. So JAR is my pre-image. Anytime I add these little apostrophes, those are called prime. So this is J prime, A prime, and R prime, and that is the image. So the pre-image is my JAR. And then the image is this J prime, A prime, R prime. So we are asking which one of these is a reflection, so a mirror image across the x-axis. So remember the x-axis, they're all the same here. You can see x, x, x. So all of those are the x-axis. So we want to know which one of these is the reflection. So that means that if R, so this one would not be right because it looks like these R and J have switched spots. On letter B, it appears that this one is a contender, so I'm going to keep going. This one, C, looks like it's shifted, so I'm going to say that's not it. And D, it looks like we've rotated it a little bit, so that's not it. So I'm going to go with letter B as my reflection across the x-axis. I think we're on number 4 now. Same as number 3, except this time we're reflecting across the y-axis. So here's that y-axis. So we're looking at where the letters are ending up. And JAR is the black figure. That is the pre-image. And we're looking to figure out where the image, J prime, A prime, R prime, ends up. So, and we want to reflect across the y-axis. So let's look at these A, B, and C. Okay, so for these guys, I'm going to zoom in a lot because the differences are really hard to spot. When I look at letter A, what I see is that the distance between the line of reflection and each of the points is different. So here the difference is 1 and here the difference is 2. So that is not a true reflection. On letter B, I see this difference here is 2 and this difference here is 3. So again, it's not a true reflection. So scooting them over, let's look at C and D. C looks like it might work, except for the fact that this little line here is a lot longer than this little line here. So this doesn't look like it. This looks like the image has been dilated. So now I'm going to check D. It looks like there's 2 here and 2 here. Okay, this looks like 1, 2, 3, 4, 1, 2, 3, 4, and 3 and 3. So I'm going to pick letter D on this guy. All right, on this one, we want to determine whether or not these things are a rigid motion or not a rigid motion. So a rigid motion, remember, preserves size and shape. So on this first one here, it appears to be a reflection here across this line of reflection. So I'm going to call this one a rigid motion. On number 2, this one, it looks like it's a rotation. So I'm going to call this a rigid motion. On this guy right here, it looks like it's a dilation. So it looks like it's changing the size. The shape is the same, but the size has changed and the new one is bigger. So this is not a rigid motion. And same thing here. These almost right here don't even look like the same shape. This is definitely a different size. Maybe they are the same shape, but they're definitely not the same size. So this is not a rigid motion. All right, now we're moving into translations. So we are taking each of these points. So image, nope, just kidding, pre-image, and this is my image. And I am going to take the ordered pair and I'm gonna add 5 to the X and 4 to the Y. So that means I'm gonna move it over 1, 2, 1, 2, 3, 4, 5 to the right, positive 5 is to the right, and up 1, 2, 3, 4. So you can do it on the graph and you can find it, or you can do it by ordered pair. So A currently is at -8. This right here is -8, and this is 5. So A is -8, positive 5. So I'm going to add 5 and I'm going to add 4. So -8 plus 5 is -3, and 5 plus 4 is 9. And if you want to verify over here, look, that guy ended up at -3, and this guy ended up at 9. So this one is going to be -3, 9. All right, now we're going to do B. So B, I'm going to do the same thing. I'm adding 1, 2, 3, 4, 5, and I'm going up 1, 2, 3, 4. So that was over 5, up 4, and that ends me right here at 2, 4. So we can double check. B starts at -3, 0. Okay, so let's add 5, add 4. -3 plus 5 is +2. 0 plus 4 is 4. 2, 4. I get the same answer. Wahoo. All right, last one, C. We're going to move C over 1, 2, 3, 4, 5. Same thing, plus 5, plus 4. Then we're going to go up 1, 2, 3, 4. So I end at 0, 3. So 0, 3. Okay, so C started at 5 and -2. C was 5 and -2. I'm going to add 5. Oh, just kidding. It started at -5, -2. So I'm going to add 5, and then I'm going to add 4. And it helps if Ms. Ender can count. 1, 2. That's 2 there. So that takes me to -5 plus 5 is 0, and -2 plus 4 is 2. So this point is 0, 2. You don't have to do it both ways, but you can. I'm just showing you different ways in case your brain works differently. Okay, so this little doohickey right here is transformation notation. So this is the same thing as saying we're going to take X and add 3 and Y and add 2. This 3 right here means +3 in the X value, and this 2 right here means +2 on the Y value. So we're looking for this image being moved 3 to the right and up 2. So who moved there? And it looks like black is our pre-image and blue is our image. So I'm going to go with B. It looks like I've moved 3 to the right and up 2. Just kidding. I'm actually going to go with letter D now that I've looked at it. This looks more like what this one would look like as far as that point down here. Let's call it A. A prime is above the x-axis. This looks like it would be below the x-axis. So I'm going to go with D as my actual choice. All right, on this one, we have to look for which figure is changing. This is the one that always messes me up. So here I am seeing that the blue figure is translation of the black figure, which means this is my pre-image and this is my image. So the black figure is the OG. This is the one that we start with. And then we need to figure out how does it move to go to the blue one. So I'm just going to take any point and there we go. That's a little better. I'm going to take any point and I'm going to count how does it change. So let's see. I'm going to take this black point right here. And I'm not even going to worry about ordered pairs. I'm just going to say it goes up 2. And it goes left 1. Okay, so left and right is our X position. So that would mean a -1 for the X position, and up and down is our Y position, so a +2 for our Y position. So that's what I want to put right here. So I want to put a -1 and a +2. Okay, this one says, what happens if we do this move and then we do this move? So all you're doing is changing this and this to something over here. So 5 minus 1 is really a net of a +4. So I'm looking for an X plus 4. And then 2 and 5, 2 plus 5 is really a net of 7, a +7. So a Y plus 7. So I'm looking for X plus 4 and Y plus 7. So that would be this guy right here. Okay, so the important part here is to remember that the distances are different. That the angle of rotation is actually the same. So this one does not work. But when I'm rotating a figure, every point doesn't move the same distance. It moves the same angle of rotation. So this is an A. Okay, so here's my little tricks on rotations. And I don't think about points. This might kind of screw you all up a little bit if you've learned it a different way, but this is what I think of. I think of which quadrant am I going to end up in? And that tells me the signs. Now I know if I rotate 90 or 270, that is going to be a swap of X and Y. So X comma Y becomes Y comma X whenever I do a 90 or a 270 rotation. 180 rotations, it's X, Y, just stays X, Y, but it changes the signs. Okay, but I don't worry about signs on these. I think about where am I going to end up. Now, rotations are always counterclockwise. So if you think about a clock, so 12, 6, 3, 9. Clocks move this way. An analog clock moves to the right, moves the direction of the right. Counterclockwise is the opposite. So I move in the direction, I rotate to the left. So if I start point D at over 0 but up 5, and I rotate it 90 degrees to the left, it's going to end up right here. So again, it's a flip-flop of the ordered pairs. So that means that my ordered pair is going to be 5, 0. Flip-flop the ordered pairs. But now, am I +5 or -5? Well, if I'm going to end up here on the x-axis and not here, that's got to be a -5. So I think about where does it work. Now, there are rules you can memorize, but I'm not a big memorizing rules. I'm more about trying to figure out what's happening. Okay, my next point, E. E is at -2 up 8. So I'm just going to kind of guess. Here's E. -2, 8. Now I'm going to rotate it 90 degrees. That means I'm going to flip-flop it. So E prime is going to get flip-flopped, and it's going to be 8, -2. But does that work? If I flip-flop, E comes down here somewhere. I don't know. But now, does 8, -2 work? No, because 8, -2 would be over here somewhere. So to get this guy, this is quadrant 3. And in quadrant 3, we are negative. So that means both of these guys have to be negative. So -8, -2 makes a better guess here. All right, and then our last one is F. So F prime is going to be flip-flopped. So -5, -3. Okay, so F is starting out at -3, -5, which is here. A rotation, 90 degrees, is going to end me in quadrant 4. Quadrant 4 is +, negative. So that means this is going to be a positive 5 and a negative 3. So in general, on these rotations, let's see. Okay, there we go. So in general, on the rotations, here's kind of what I do. If it's 180, x, y just becomes negative x, negative y. Pretty simple. If it's 90 or 270, that means that x, y switches. So it becomes yx. But then I have to figure out the signs. So a 90-degree rotation, if I start in quadrant 1, which is positive, positive, I end in quadrant 2, which is negative, positive. If I start in quadrant 2, which is negative, positive, and I do 90-degree rotation, I end in quadrant 3, which is negative, negative. If I start in quadrant 3, which is negative, negative, then I end in quadrant 4, which is positive, negative. Okay, now that's a 90-degree. 270-degree rotation goes this way. Okay, so I go through 3 quadrants to do 270, and I go through 1 quadrant to go 90, and I go through 2 quadrants to do 180. That's why the 180s flip-flop signs. See? Positive, so if I went through 2 quadrants, quadrant 1, quadrant 2, I flip-flop the signs. If I went through these 2 quadrants, I flip-flop my signs. All right, so here's a 180 rotation. So this one, let's do just flip-flop signs. So it's going to be 2, 6, 5, negative 3, and negative 1, 0. Just flip-flop signs. That's it. For 180s, it's easy. 360 is silly, but we'll do it anyways. 360 degrees. So if I started in quadrant 1 and I went 360 degrees counterclockwise, I end up at exactly the same spot because it is a full circle. So these are all the same. Nothing changes. Okay, so a glide reflection means that I am going to reflect and then glide. When I do a composition of transformations, I work from the right to the left, so going this direction instead of left to right. So because it says reflection second and it says glide first, it goes reflect, then glide. I know that seems kind of silly, but I will tell you that when you get into Algebra 2, compositions are going to work exactly the same way. You're going to go right to left or inside out, so that's kind of preparing you for that. So this guy is going to take, here's my pre-image. So first I got to reflect it, so it's going to be over here somewhere, and then I got to glide it. So the one that looks like that for me is letter C. So reflected here, and then a slide down. Okay, so again, this one's going to be a glide reflection. I know that because R, Q is to the left of R to start, and Q ends up to the right of R. So it looks like it has flipped, and it looks like it's flipped across this line. I know that's the line of reflection because I'm 2 units away here, and I'm 2 units away here. So in a reflection, I am the same distance from the line of reflection, both on the left and the right, or on the top and the bottom. So I know I'm a reflection across the y-axis. So that's this guy and this guy. That means this and this are not going to work. But then I need to figure out where do I slide. So here's where R prime would be if I reflected. And then how much do I glide down or translate? 1, 2, 3, 4, 5, 6. So 6 down would be letter B. 6 down. This guy right here. Okay, symmetry means the same on both sides. So if I were to fold it in half, would I have symmetry? And so this figure actually only has 1 line of symmetry. It's kind of boring. Well, let's think about that again. So this would be a line of symmetry. Just kidding, it has more than 1. This would be a line of symmetry if I folded it in half, and this would be a line of symmetry. So this guy should have 3 lines of symmetry. So how many lines can I make where I fold it in half and I get the exact same thing on either side? If I were to fold in half right here, that would give me, this side would match this side. If I were to fold it in half along this line, That would also, this side would match this side. And then last, if I folded it in half here, then the two sides would match. So I have 1, 2, 3 lines of symmetry. Okay, so how many lines of symmetry? So this one you could use like a piece of paper. So take a rectangular piece of paper, which is any loose leaf. There should be some in the drawer over on the table for your all's use, unless you've used it all since I've been gone. And then start looking at, just fold it along the dotted lines. So fold it on the diagonal. They're not going to match up. It's going to end up with like, see if I can draw it. It's going to end up like this. If you fold it over here, like these corners aren't going to match. So this isn't an option. Now here, this fold in half this way, that's symmetry. And then if I folded it in half this way, that's symmetry. This has both A and B. Well, if A doesn't work, then both A and B is not going to work. So this is only letter C. All right, again, I'm looking to see which one of these is going to match when I folded it in half. This one looks like it might, or you might intuitively think so, but if I fold this top A over, let's see if I'll blow it up here. Okay, oh, just kidding, there it goes. If I fold this top A over this line of reflection, so if I take an A and I fold it over a line of reflection, it's gonna go like this, which is not perfect. Same thing on these other guys. Now this one is promising. If I fold here, then this M is going to match this M, and this A is going to match this A. Now it doesn't happen with every letter or every word that does that. They have a special name. I can't remember what it's called. But it doesn't happen with all of those. It just happens like that because this A is symmetric vertically. All right, so which one will transform and map the figure back onto itself? So if I reflect through a vertical line that goes through the top and bottom, do those match? Heck yeah, they do. Let's see, what's the next one? If I rotate this figure 180 degrees, so 180 degrees, is that going to match? 180 degree rotation about the bottom vertex of the figure followed by a translation up. So if I took this as the vertex and I rotated it, let me redo that. Took this vertex, rotated it so it went like this, and then I translated it back up. Am I going to map? Yes. What about letter C? Let's see. If I reflect it across a horizontal line that passes through the left and right vertices like this, that would match as well. Okay, keep going. A 270 degree rotation, so about the right vertex, so here, 270 degree rotation, so that means I'm going to go counterclockwise through sorry, my iPad glitched. So using this as the rotational point, I'm going to go 270, so that means I'm going to end up back over here. So if I did that, let's see. All right, there we go. That would be 270 rotation about the right vertex, and then translate it to the left. That is not going to map. And then a 90 degree rotation, again, is going to give me this kind of horizontal guy. It's going to be this way instead. And then a translation, it doesn't matter where I translate it, it's off. So this for me is A, B, and C. All right, last one, and this is my favorite one. Which letter can be mapped onto itself by 180 degree rotation about its center? So that means that the center point, so let's say this is the center point. If I flipped it upside down, is that going to work? Nope. About the center point, let's see if I flip that guy upside down. Will that work? Nope. If I take this guy and I rotate it 180 degrees, so taking my iPad and turning it upside down, or let's see if I can do this guy. Hold on. I got to unlock my rotation. Okay, now let's see. If I rotated this picture upside down, ooh, that's a really good visual. Which one of these looks exactly the same? Hey, that makes it easy to see. N is the only one that still looks like the letter N. All right, guys, so that is it. That is everything that you need to do for your test. All the questions will be the same with different numbers or different points, except for some of them which are going to be identical. So I hope that you study this, and I will see you guys the week of Thanksgiving. Thank you.